When the ground beneath our feet starts to shake with just an unimaginable force, our first instinct is to look to our buildings for safety, right? But how can a structure made of concrete and steel possibly stand up to the power of a major earthquake? Well, let's dive into the incredible and often hidden science that makes it all possible. You know, this quote, it's a really powerful and, honestly, a sobering truth in the world of structural engineering. It means the real fight isn't against the earthquake itself. It's against gravity and the failure of the things we build. And that's a fight we can actually win with smart design. So how do we do it? To answer that, we're going to follow the design journey of a single specific building, a pretty standard 4-story office block. We're going to see exactly what engineers have to calculate to make sure it can ride out the storm when the big one hits. Okay, so where do you even begin? The very first step for any engineer is to answer one critical question. When an earthquake hits, how hard exactly is it going to push the building sideways? This first calculation is called a static analysis, and it gives us one single vital number to start with. Now, our building isn't just some theoretical model. It's being designed for a real place, Shillong, India. This city is located in what's called Seismic Zone 5. That is the highest risk category there is. So that makes all the calculations we're about to see incredibly high stakes. This is the real deal. All right, so to find that total push, what engineers call the base shear, they plug in a few key factors. First up, the seismic zone. For Zone 5, that's a high 0.36. Then you've got its importance. Since it's just a standard office, that's a 1.0. Next is how it's built. For a modern reinforced concrete frame, that factor is 5. And finally, you need the building's total weight, which is a whopping 15,600 kilonewtons. You put all that together, and you get this, 1,404 kilonewtons. Now, what does that even mean? To put that in perspective for you, that's like having more than 100 cars lined up, all pushing against the base of the building at the exact same time. That is the kind of force we have to design against. But here's the thing. A building isn't just a solid, rigid block. It's got some flex, it sways, it vibrates, it basically wobbles. And a simple push number doesn't really capture that complex movement. For that, we need a much more sophisticated approach called dynamic analysis. So what's the real difference here? Well, the static analysis we just did, it's a great starting point, giving us one big number for the total force. But dynamic analysis, that's like a whole other level. It creates a complex computer model that simulates how the entire structure bends and flexes in all these different patterns, or modes, during a quake. It's just way more realistic. And just look at what it tells us. This table compares the force on each floor from both methods. The simple static analysis assumes the most force is way up at the top. But look at the dynamic analysis. It shows the force on the roof is actually lower, while the forces on the first and second floors are way, way higher. That's an absolutely critical difference when you're designing the columns for those lower floors. Okay, so we've got the push, we've got the wobble, but there's another hidden danger that we have to account for. A really deadly twisting motion called torsion. This happens when a building's layout isn't perfectly symmetrical. To understand torsion, you gotta get two quick concepts. First is the center of mass. Just think of it like the building's balance point. If you could somehow balance the whole structure on the tip of a giant pencil, this is the exact spot where it wouldn't fall over. The second key point is the center of stiffness. Now, this isn't about weight, it's all about strength. This is the building's structural heart, the single point where all the columns and walls work together to offer the most resistance to being pushed sideways. So here's where the trouble starts. In a perfectly designed, perfectly symmetrical building, those two centers are in the exact same spot. But in the real world, that almost never happens. So when an earthquake pushes on the center of mass, the weight, but the building resists from its center of stiffness, the strength, and those 2 points aren't aligned, the building twists. And here's what that twist does. Because of torsion, the load isn't shared equally anymore. In this building, wall B, over there on the far side of the twist, has to handle nearly 72 kilonewtons of force, while wall A only sees about 43. That is a massive difference. It's exactly why you see so much damage on the corners of buildings after an earthquake. Torsion puts incredible stress there. But we're not done yet. Not even close. Great engineering is all about sweating the small stuff, accounting for the messy details of the real world. So let's do a quick lightning round of reality checks that designers have to factor in. First off, concrete isn't perfect. It's not a perfectly rigid material. Under the huge stress of a quake, it's going to develop tiny cracks. Engineers know this is going to happen, so they don't even use the material's full theoretical stiffness in their models. They use a reduced, more realistic value, basically planning for imperfection right from the start. Second reality check. See those brick walls between the concrete columns? You might think they're just dividers, but they're not. They actually act like giant diagonal braces, and they add a huge amount of stiffness to the building. If you ignored them, you'd get a totally wrong idea of how the building will behave, so their strength has to be included in the models. And third, it's not just the building itself you have to worry about, it's everything attached to it. Take a heavy piece of equipment, like a 100 kilonewton generator sitting up on the roof. If that thing isn't anchored down properly, it can become a massive, dangerous projectile. So the forces on these items have to be calculated too. So we've looked at the push, the wobble, the twist, and all these nitty-gritty real-world details. The one thing that brings all this complex science together is the seismic design code. It's like an invisible rulebook that makes sure every single part of this analysis gets done right. So let's just retrace our building's journey. We started by calculating the total push. Then we made that way smarter with a dynamic analysis to see how it really moves. We accounted for the dangerous twist of torsion, and then we layered in all those real-world details. The end result isn't just a strong building. It's an intelligent one designed to work with the forces of an earthquake, not just fight them. And maybe the coolest part is that this science is always getting better. Seismic codes aren't set in stone. After every single major earthquake, anywhere in the world, engineers study what went wrong and what went right. They use that knowledge to update and improve the codes, making the next generation of buildings even safer. Which really leaves us with a final thought. We're building bigger, taller, and more complex structures than ever before. So as we keep pushing the boundaries of what's possible, the invisible science of seismic engineering will have to evolve right alongside it, constantly learning and adapting to keep all of us safe on shaky ground.